Hey, here we are, and thanks for jumping in on this. If you're watching this, please make sure that you have Eclipse installed so that you can do the examples and get familiar with that IDE. This is an overview of data structures and algorithms. It's a class that I've taught a lot, and if you're watching this before you take your next class or your data structures class, I hope it'll help. Like I said, this was one of the classes that I taught a lot in the college levels at several universities. So I'm just going to go over a couple things, and there's a lot. So it's kind of fun. It's a neat thing, and it's a good tool to have. And if you can get some of these things before you take this class, if you watch this and just kind of understand some of these things that I'm putting out there, you can always email me. I'll make sure that I have an email link for you if you don't already have my email. Then I'll answer any questions you have. So let's go over what this is. Okay, and we're going to talk today, or this lecture, we're not going to do any coding. We're just going to talk about a thing about data structures and algorithms. And then the next lectures, we'll get into different codes. So let's just talk about what's going to happen during these series. So there's going to be a fair amount of videos. This will probably be, there'll be a lot of them because it's a big class. All right, so let's get started. What is this? It's just going to cover classic algorithms and data structures. And we're going to look at some real world computational problems. We're going to focus on algorithms for sorting, searching, string processing, and graphs. Okay, and different algorithms along the way, right? Diffie-Hellman, Dijkstra, A-star, things like that. You're going to learn the basic strategies to evaluate, divide, and conquer, recursive backtracking, algorithm efficiencies. We're going to have some activities for you to work on. Different code, implementations of algorithms. It's what you're going to get into when you get into computer science and software development. Without this class, you don't move forward. Every university has their version of it. So the first thing we're going to do is we're just going to talk about array structures. And arrays are comfortable. We like arrays. We know arrays. That's our first data structure, right? We get introduced to arrays and array list or vectors, and we're like, okay, I understand. I like arrays. It's a container. It's linear. I can do things with it. It stores stuff. I like arrays. We're going to talk a little bit more in depth about what the array is and how it works. And then we're going to move into a thing called a singly linked list and a doubly linked list. And a singly linked list is going to be your vectors or your array lists. So array structures are static. They're just one size. Boom, you make an array and that's the size it is. Singly linked list is dynamic, right? It's linear, it's a dynamic thing. We're going to talk about stacks and queues. We're going to talk about recursion. Recursion is super easy, I promise you. It's cool as can be. We're going to talk about trees and heaps. It's super powerful. Trees and heaps are powerful. We're going to talk about hash tables and what hashing is and hash tables. I'll decide as we go on. Normally, when I teach this class, we build our own data structures, right? We write our own data structures. Now, every language is going to have like an array list or singly linked list in there, right? Every language is in the library is going to have a stack and a queue pre-built for you to use, so you can use these things. Everyone is going to have a tree or different types of trees or sets or maps, as they're called. And every one is going to have a different hashing table or a dictionary, and everybody's going to have a style of graph. Not really, well, some graphs, but graphs are cool. So I like to know how these work by actually building our own. So we'll talk about the differences of a custom built one and one that's already in the library for you to use. All right, so those are what I want to cover. These are the little things we're going to work with. We're going to do a quick array warm-up. We're going to talk about populating an array, sorting the array using a very inefficient bubble sort, and then a binary search. We're going to talk about singly linked lists, some doubly linked lists, a maze solver, which is pretty cool, recursive stuff, simple BST or binary search tree. We're going to build a hash table, and we're going to deal with graphs. So all these will build code to make these things work throughout the class, right? So throughout these lectures, we're gonna go over, hey, let's see how these are and what they are, and it's cool that way. So array structures, this is what we're going to start with. Array structures, like I said, arrays are comfortable. We like arrays. And we're going to implement a string data type using arrays as the underlying structure. And we're going to do an algorithm using loop and variance to evaluate big O notation. And that's what today is about. We're just going to jump right in and we're going to talk about this thing right here. That's my laser pointer. This right here. Big O notation. This is going to be part of every single thing that we do. If you can get a comfortable understanding of big O, and I'm going to mention it on every single thing that we do. If we could talk about big O and you can go into your class, your algorithms class, and say, hey, I have a vague understanding, I have a decent understanding of big O. Now we're not going to go into the math and the calculations of it. You haven't taken linear, you haven't taken discrete. So the actual asymptotic notation is a little heavy, but I can teach you big O and how to identify it and how to find what your big O is. So let's just start there. Okay, that's what this is going to be about. But don't get bored. It's super cool. Now, what is big O? Well, you can look up the big O cheat sheet, right? Because the big O cheat sheet is cool. So with the big O cheat sheet, and I'll bring that up. Let's see if we can bring that up. Anyways, I'll bring it up on the next slide. Anyways, we'll bring up the big O cheat sheet. This is a simplified analysis of algorithmic efficiency. So when you develop an algorithm, your algorithm is only as good as efficient as it can be. So if your algorithm is inefficient, it's not a good algorithm. So what do? This is a way to calculate algorithm efficiency. We identify the efficiency in big O. And this makes complexity in terms of input size, n. So n is going to be the amount of input size. We don't know how our algorithm we build. So we're building an algorithm that just solves a problem. We don't know how much input we have. It could be a little bit of input. It could be a large amount of input. And it doesn't matter because we can calculate it based on just n. N can be any size. Big O is machine independent. It's very code independent too. So big O in Python is the same as Java and C++. So it doesn't matter. Big O is code independent and machine independent. It doesn't matter what machine you run it on. It's still the efficiency of that. It's the basic computer steps of the code. And we use big O to analyze time and space. Computer resources. Not like time and space and it's there. But computer resources. So big O is used for computer resources. There are some problems that we have in the world that we can't fix yet because we know how to fix it. It's just too inefficient for us to run. All right, so let's go backwards a little bit. What is big O? Anyone we know are concerned about big O. As your career as a programmer grows, you need to know two things about your program, application, or game. Two things. You get to a technical interview or you start interviewing for a job, they're going to want you to know efficiency. That's it, right? You're doing lead code. Lead code's all about efficiency. Two things you need to know, time and space. Big O is what we use to identify how long an algorithm takes to run. So, being over simple, runtime is expressed on how quickly it is relative to input. Okay, so that's our key, relative to input. How efficient are you relative to input? So big O lets us measure things. Okay, types of measurement. Okay, well let's come back to this. I'm going to come back to this slide. I want to go to the big O cheat sheet. 1 second. Okay, here we are. I know it's just kind of thrown in there, but let's just talk about this really quick. This is the big O cheat sheet. All right, and we're going to look at these things: O to the n exponential, O to 2 to the power of n, O to n to the power of 2, so that's n squared. This is pretty much where a lot of our stuff runs. N log n, O to the n, O to the log n, and O to the 1. These are some of the things that we have, our data structures, and what they run with. So we see an array, the access is O to the 1 if we know where to look. If we don't know where to look, searching is O to the n. And these will make sense once we're done talking about it. But this is a great little resource to have. Just look up big O cheat sheet, and you can use this to identify how fast some of your algorithms will run. We have our sorting algorithms right here. Look, we have our bubble sort. We're going to do these 3 sorts on the next lecture: bubble, insertion, and selection sort. And you notice they run in the red. See, they run a polynomial or n squared. and that is average and worst. Best case is O to the n, but that's only if it's already sorted when you get it. Okay, so these are pretty cool. So the Big O cheat sheet is really, really important, and it's a good thing to have you do. There's some fun coding interviews, things to do with. This is a great little book. This is also a great little book, Data Structures and Algorithms in Java, 2nd edition. So this is just a great resource for you to have getting ready for your next class. All right, back to the lecture. I just like to share that because I use it a lot. Okay, I'm back. I just showed you the Big O cheat sheet, and now let's explain that, okay? Because some of that's like you're looking at it and like, I don't get this. Why are you showing it to me? I'm not ready for this. You will be. Trust me. You're all very smart. Okay, so the types of measurement. We saw this in the Big O cheat sheet. There's the worst case, best case, and average case. We are always concerned with the worst case. That's what we're concerned with, the worst case. We always go to the worst case. A lot of algorithms that are really, really inefficient will work on the best and average case, but we want to make the worst case. So we always identify the worst case of our algorithm efficiency. That's just what we do. We're not doomsday people, but that's how we identify our algorithm efficiency. So let's talk about the general rules. Remember, n is input, okay? So our general rules of understanding Big O. Now this is the general rules without having to do the mathematical calculations. So these are general rules. So you can look at an algorithm and this will help you find it. Ignore constants, okay? 5n doesn't matter, okay? So ignore constants, and I'll be more available about what constants are. Here's a quick constant. If I assign a variable x equals 5, that's a constant. There is no, that's just O to the 1. It just happens in real time. There's no, this is not dependent on n at all, okay? Doesn't matter what we assign it, as long as it's an integer, it gets assigned to x, O to the 1. Certain terms dominate others. So O to the 1 is best case for everything that we do, and that is a constant, O to the 1. This is O to the 1, because it doesn't rely on n, okay? What I mean by dominate others is lower terms always get ignored. So if I have a whole bunch of variable declarations, those are O to the 1. They're going to get ignored the minute I have O to the log n. Okay, you don't add these things. You find the worst case in your whole program, the algorithm that's the worst, and that is the big O for your application, right? So O to the 1 is a constant, O to the log n, O to the n, right? And that's just O to the n, that's pretty good. O to the n log n, O to the n squared. This is where we get nested loops. O to 2 to the power of n, that's getting pretty bad. And O to the exponential growth, and this is the very worst case. If we get to O to the exponential growth, your application won't run. Too much resources, can't compete. All right, so wherever we start adding on to these things and identifying which one of these big O's we're at, we ignore the lower terms. Just stay with me. Constant time of big O is O to the 1. This is constant time. Algorithms will always execute the same time or space regardless of data input. So regardless of the data, it's going to run at O to the 1. Okay? So x equals 5 plus 15 times 20. It's independent of n. There's no n. There's no, I can't add n to this. It's just assigning value to x. This just runs in O to the 1 time. So several constants, O to the 1, O to the 1. I'm just assigning variables. If I print it, okay, total times O to the 1, O to the 1, O to the 1, 3 times O to the 1. Well, it doesn't matter. We drop the constants. Okay? So if I just had a program that assigned value to x and y and printed it, it's O to the 1. It's independent of input, multiple inputs. Okay? So that's it. Assigning variables, running if statements, printing, all those are O to the 1. Okay? Linear time. Time complexity grows in direct proportion to the size of input data n. So let's look at this. This is a for loop. We know what a for loop is. A loop is going to run as long as we tell it to run. Here. It is dependent on this value. This for loop runs as long as we tell it to. So if n is 1, it runs 1 time. Not a very good for loop. If n is 10, it runs 10 times. If n is 1 billion, it runs 1 billion times. This is a loop which is dependent on input, or on what we call n. Not just input, but n. So this can be a variable or it can be a number, but a for loop runs as long as we tell it to. This is O to the 1, right? But this is O to the n. See? Just regular loop. So this is O to the n. So I have O to the 1 right here, and then O to the n. This is a regular for loop is O to the n. Big O to the n. Stay with me. We're going to do this for a lot of videos. This is O to the 1, right? I'm just assigning y a value. Well, this is O to the n because it's going to run dependent on that y value. We kick out lower terms, O to the 1. A regular for loop, just put this in your head. A regular for loop runs O to the n. There you go. That's our for loop, runs O to the n. Okay? All loops are not linear. Okay, if we look at that for loops we had, they just start at 0 and go to whatever we tell them to, right? I into 0 goes to n. If n is 5, it runs 5 times. If the algorithm is going through an array looking for a specific reference point in the array, it's a constant time, not linear. It's independent of the size of the data structure, just finding a specific index. So time is constant. For a linear measurable time, the algorithm will interact with each index, or part of that data structure. Unless that data structure only has one index, that only demonstrates the growth of input. Now there's a lot of word salad in there, but really what I'm just trying to say is if I'm using a for loop to go through, let's say I have an array, and I'll make it small. 0, 1, 2, 3. If I loop through the array and print out everything in my array, I have to touch each one of these, right? That's O to the n. If I know that I just want to put the value of the array, we'll go foo. If I just go print foo to the 2, index 2, that is O to the 1 because I know exactly where I'm going. Okay. If I want to skip every other one and I go int n and then my loop invariant, I have I equals 0, I is less than n. Instead of I++, I don't want to do I++, I'm going to do plus equals 2. Well, that's not going to touch every single one, right? That's going to skip, so that is going to be more efficient because it's not going to hit every single index. Worst case, I still don't hit every index because my invariant skips. It's not one-to-one, linear across. It's going to be a lot today. Make sure you get through the lecture, and then we're just going to keep coming back to it. But I want to introduce Big O to you. Hey, everybody, Big O, everybody, and then you guys can become better friends in the next 7 or 8 videos. All right? So that's linear. Quadratic time represents an algorithm whose performance is directly proportional to the squared size of input. Okay, so if you have a nested loop, I is 10, j is 5. We know nested loops, this gives access, and this has to go through iteration. We know to calculate nested loops, we take the outer number of times that it runs times the inner number of times. This will run 50 times because it's n squared. This times this. Now ignore I and j. Let's say this is n and this is n. Well, n times n. Well, if n times n, that's n squared. So if this ran 20 times and this ran 5 times, right? 5 times 20, that would be 100 times. This would run 100 times. N times n. And this is a nested loop. What happens is this loop runs once, and this loop runs 5 times, and then this loop leaves, and it comes back. This runs again, and this starts all over again because we reinitialize j. So this inner loop is going to run this times that. So nested loops are always going to be n squared. This is a result of Big O. Okay, n squared. So a single loop is O to the n, a nested loop is n squared. That's pretty cool, right? And that's called quadratic time. Now it's a lot. Okay, so we're going to take a little detour. We're going to explain this a little bit better, ideally through Secret Tunnel. So let's go ahead and learn a little bit more about Big O. All right, Oh, Kangaroo Island. That's a hop in place. Anyways, sorry. That slide was left over from another lecture that I did for a class on this. All right. Slide lecture on Big O. Okay. Mostly we're concerned with Big O and its worst case relationship to our algorithms. Okay. I hope you have a better understanding. Now there's other ones. There's Big Theta, Big Omega. We're just going to discuss Big O. We'll get to Big Theta and Big Omega later. All right. Asymptotic notations. You can look it up. A function, its approach given the value of an expression containing a variable tends to infinity. That's a single function. Of two functions, so defined that the ratio approaches unity as the independent variable approaches the limit. Of a formula becoming increasingly exact as the variable approaches the limit, usually in infinity. Coming into consideration as the variable approaches the limit, now we have asymptotic properties and asymptotic behaviors. Now this is what I'm trying to get away from. Okay, these, you'll get to these later in your academic career. Right now, let's just understand Big O a little bit. But I don't want you to like, oh, I'm going to learn Big O, and then you start reading this and you're like, I'm not going to learn Big O. So don't worry about this. Remember this. It is impossible to truly analyze the time and space complexity of an algorithm. As programmers, we need standard notation. In computer scientists, it's known as asymptotic notations. So think about any algorithm you develop. It is possible to find variable declarations, memory that we allocate, lines of code, function calls, memory, amount of iterations, and so on. Those are the predictable parts of the program. If we just added up what we knew about an algorithm, we'd be able to find value. Okay, that's fine, right? If I read code, and I read a ton of code, if I read code, I can tell you how much memory you've allocated, what your resources are going to be, all these things. And that's fine as far as it's written. It does not help me at runtime. I need a way to determine how your algorithm is efficient at runtime. Okay? So a quadratic equation is a common equation in nested loops. That's their n squared. We talked about it. So time versus n, number of elements in the array. So time times n equals n squared plus 2n plus 6. Time is calculated to 2n plus 6 are linear times and have no real effect on time, right? These don't have any effect on time. 2n is the time hog, and it grows faster than 2 times n plus 6. So we only want to look at 2n, right? This is how we look at this and we say, okay, these don't count. Because let's say I take n and I make n 6. Well, 6 squared is going to be bigger than 2 times 6. That's just simple. 10 squared is bigger than 2 times 10. So anytime I have a larger n value, right, these don't matter. Those are never going to catch up to this as the algorithm runs. This is why we're not concerned about constants, and higher orders are promoted. Remember, ignore constants. Certain terms dominate others. We get to our worst case, you're doomed. Okay? But a constant time is going to get dwarfed by n squared. A constant time is going to get dwarfed by O to the n. There's not even n here. Okay? So ignore O to the 1, and the worst case is n squared. If you have this as your algorithm, this is n squared, and this is O to the 1, that's going to be n squared. That's our behavior. There are 3 types of asymptotic notations. We have Big O, Big Theta, and Big Omega. So let's talk about which ones are which. Big O is upper bounds. Okay, let's look at the order of pizza. We have 3 ways to get our pizza delivery ordered in time. We can use Big O, and it says your pizza will arrive before the end of time. I order pizza, and the guy says, okay, it'll be there before the time is over. Big Theta is tight bounds, meaning we know exactly. Your pizza is going to be there between 4 and 6. Not exactly, but it's going to be there in this time frame. Big O is worst case, right? Worst case is, hey, you'll eventually get your pizza before the world ends. Big Theta says, hey, we'll be there in about 4 to 6 minutes. Big Omega is lower bounds. You call while you're dialing the phone, your pizza is delivered. That's pretty cool. So Big Omega is like ideal, and that's one of those kind of fantasy things. Big theta is tight bounds. We use big theta a little bit more these days because we can do better things. We have better computers. But big O is still what we're worried about. Now remember, big O is worst case. Worst case, worst case, worst case. And that's what we want. So big O, upper bounds, worst case. Certain functions will never exceed specific time of any value of input n. Okay, n is the determining factor of big O. So let's explain. I have an array. Okay, it has n number of elements in it, right? Looping through is linear, one element at a time. This will go through, no matter how big my array is, this will start at 0 and go through every single element. Worst case, we start at let's say I'm looking for something. So if I'm looking for something in my array, and I'm looking for the number 5, and worst case is I have to go through the whole thing to get there. That's the worst case. If I knew it was at 0, 1, 2, 3, 4, if I knew it was at element 5, I could just find it, and that's best case. But that would be linear, right? Because that's order 1. I'm just assigning value, and x equals foo to the 5th element. Worst case, I have to loop through to find it. And that's the worst case. Why do we use big O's? If we type bind with big theta, the linear complexity is directly related to n. Then we know n. So big theta is you know exactly how much input you're going to have. And you can calculate theta that way. But we don't, at runtime, we really don't. We use time complexity. Big O is O to the n. O to the n with big O, the complexity will never exceed n. Okay? And what do we mean by that? Well, it means that we'll never go past n because n is our input. N is the number that we don't know. It could be, our loop could go I is less than n, but it'll never go more than n. You can't go beyond the size of your array. Big theta, same rules, ignore constants. Big theta is like the average value or range the actual time execution will be. We type bind between two constants, calculating the average time on each. We're not going to do that on this class. Big O is best case, simple enough. Algorithm may take more time to resolve, but the best case is always big omega. I have a 2D array, and I'm looking for something that's at index 0, 0. Best case. So a big omega, lower bounds, best case, all the information I need is going to be right where I need it, right? So my algorithm just is done. It's predictable. You're giving the algorithm an already finished problem. Algorithms solve problems. If you're doing big omega, you've given the algorithm the solved problem. Now, space. We talked about time and space. We'll go through the space pretty quick, and then this will be this lecture. I know it's kind of dry, but you should know big O a little bit. We'll talk more about it. Space complexity is the amount of memory used by the algorithm to retrieve the result. It's pretty simple. Memory is used during algorithm execution for 3 reasons: data space, compiler instructions, and native stack. Okay, so data space, we know whenever we declare variables and stuff like that, we're going to get our data space. Int x equals 5, x is going to take up 4 bytes of memory. So we know variables and constants is going to take up data space. Compiler instructions also takes up space. Native stack is recursive of function calls inside of a function. So that's how we can determine space, right? If you build a super big program and you try it running on a computer that can't handle it, you don't have enough space, right? So you need those things. Calculating the space is more concerned with data space. Knowing data types and how much memory is given is helpful in calculating space. So look, I have a little function called sum, and I declare 3 variables, x, q, w, and r. And then I just return them all adding each other. Well, let's look at this. 4 bytes for this, 4 bytes to declare the integer sum, and 4 bytes for the return. There we go. So 4 bytes for that. 20 bytes, easy to find. I just calculated my space. This function is going to take 20 bytes of memory. Easy. Now, when the function's done, my 20 bytes of memory can be released back to be used again because the function pops off the native stack. Rarely are algorithms just adding up integers. They solve problems. An array has length. This is represented by n. Now we're going to get to O to the n. Okay, there's my integer, another declared integer, and then n. int I, n, and it's just going to add some and build this up. This loops through the array starting at 0 going to the size of n. So this is O to the n. For the array is 4 bytes times n. You see that? We don't know how big the array is because it's n. It's a variable. So for the array, it's 4 bytes times n. 4 bytes for each integer sum, I, n, and return. So we have 4 times n plus 12. Linear space complexity dependent on n. This would run at O to the n. But space calculated is dependent on n. 4 times the size of the array, because it's an integer, it's 4 bytes per integer, plus 12, because we've declared 12. Okay? 4 bytes for each integer and sum, and the return, if it runs 4 times. All dependent on n. As the complexity of algorithms grows, so does your space complexity. Quadratic O to the n squares happen. O to the log is better. Try to develop space complexity low. This is good for your interview questions when you start getting interviews for internships. You're going to need to know your big O. You just will. Otherwise, you're not going to be working. Hey, look, it's saying, all right, there are a lot of solutions to any problem. Some are bad while others are good. If we're as a class meet for lunch, everyone will have different solutions on where to meet and when. So lots of N. Let's say, hey, I want to meet everybody for lunch. Everybody's going to want to go somewhere different. Everybody has input. Everybody's input is in. Some are good, some are not good. I decide what's the best solution because I'm the teacher, so I want tacos. I could ask everyone to write a function that returns the square of a number. So if I said, hey, in your mind, write a function that returns the square of a number. Okay, that's pretty simple, right? You would just take n times n, return, right? N times n, linear, O to the 1. Good job, right? But I think differently. So I think that repeated addition. So I could write something that a function that returns the square of a number by doing repeated addition in a loop. And that would be O to the n. But if you just wrote return n times n, no looped, O to the 1. See that? If you can get away without a loop and make it constant, that's how you can write more efficient. Okay? If there's another solution. Time complexity is more difficult to identify than space. Big O is a platform and language dependent. We don't calculate with the timer. Time complexity is calculated as the algorithm unfolds. We count the number of steps it takes to solve the problem. The first example of a loop is to find the square is dependent on the size of the number. The second, you just have time of 1. It doesn't care how big the integer is, it just returns a value. So if I run a loop that that runs by n and it adds everything up and then just returns that, that's O to the n because I have a loop. But if it doesn't matter how big it is, if I just take n times n, it doesn't matter if you put in 5. If I want the square of 5, 5 times 5. If I want the square of 1,000, 1,000 times 1,000. That doesn't matter. We're just calculating and returning it. That's O to the 1. Much more efficient. Big O looks for the worst case using a single binary operator, and constant times don't matter. So if you get past O to the 1, if your thing has anything besides assigning variables and printing, you're going to be moving to log n log n, or n. Okay? Most cases we're concerned with just big O. Remember, remove all constants and find n. Look for loops. Look for loops. And some loops are going to run more efficiently than other loops, right? So you just got to look for and we'll discuss loop invariance as we go through and we do more programming. The next lecture is we're going to start getting into algorithms and things like that. But we have to know what big O is, because if you don't know what big O is, you're not going to do well in your class. If I'm just assigning a variable, it's O to the 1. Okay? But if I find a loop, look for O to the n. If it's a nested loop, it's n squared. Okay? If we throw it into a loop, right, it's dependent on this. So that's O to the n. If we have a nested loop, it's n squared. You can have a for loop with a while loop inside of it, n squared. For loop and for loop, n squared. If you have for loop, for loop, for loop, right? Now you're getting O to 2 to the power of n. And that's going to be much less efficient. Then you start getting into exponential time, and it just awful. So here's weird. These are from a best case to worst case. Best case is constant time, log n, which is just a loop, n log n, where if you're thinking about a nested loop, there might be a way that you can do a binary structure or some sort of recursive structure to get it down to n log n. If we get to 2 to the power of n, that's getting into really bad efficiency. And if you have n with exponential growth, you're doomed. Your program's bad. All right, that's a quick run on what it is, right? So let's look at a quick recap, and then we'll be done with this. And then join me for the next one. Don't let this one discourage you from watching the other ones. But man, if you know big N and you go into your class and the teacher's like, "What's big N?" You're like, "It's algorithm efficiency. It's machine independent. It's code independent, and constants don't matter. And we always promote the higher term. And a lot of things are n squared with a nested loop, but linear is O to the n, and you will be the teacher's pet. And they probably won't even ask you to finish the course. They'll just give you an A and let you go and give you ice cream money." So time complexity is relative to the statement, okay? Now it does not involve n. Assigning variables, if statements, prints. O to the n, time complexity of a single loop. Log n, time complexity is determined by some sort of change in the invariant. So let's look at this. I is 0, I is going to run n, okay? Now if this is just I plus plus, it would be O to the n. But what am I doing here? I'm changing the invariant. That's this right here. So it's going to run at a different. It's not going to run on. It's not going to touch each element. This is going to make I. This is going to take n and divide n and get n faster. O to the log n, same thing. Okay, we're changing the invariant here, and n squared is a nested loop of some sort. All right, thanks for sticking through this. I owe you 38 minutes of your life back. I'll get it back to you, I promise, in the other videos. And if you stay with me on this and you go to your next class, you're going to do very, very well, I promise. I'll make sure I get my email and stuff down there in the links. So if you have any questions, you can reach out during any time during this. All right, good job, everybody.